Alright, let's take a look at this theorem or this circuit and use Norton's theorem to solve for I naught. Okay, so we want to figure out what I naught is here, going from terminal A to terminal B, or node A to node B, and we want to figure out what the current is there. Now remember, using Norton's theorem is very similar to Thevenin's equivalent theorem. We have this relationship. V Thevenin is the impedance times the current, and Z Thevenin, or the Thevenin impedance, is actually equal to the Thevenin or the Norton impedance. Okay, and this is how we are going to be working with this circuit. So we have a circuit in here, and we're looking at the nodes there, or the terminals A and B, and we can determine the Norton equivalent circuit by transforming it into a current with some impedance in parallel. Okay, and that's how we get IN. So to begin with this problem, our first goal is to look at the Norton equivalent at A and B here. And to do that, so we want to figure out Zn, or our Z impedance Norton, which is the same way we do for Z Thevenin. And to do that, we need to set those sources equal to 0. So we got to take our voltage source, turn that off, and take our current source and turn that off. Now when we set the voltage source to 0, essentially what happens is we get a short circuit. Okay, so here we get a short circuit. And when we set the current source to 0, in this case we get an open circuit. Okay, so that's the first thing we do to try to get Zn. Okay, and that's what we're trying to solve for now, is Zn. So if we look at the circuit here, the first step is to get the Norton impedance. We set the sources to 0, and this is what the circuit turns into. Okay, it turns into this guy here. And if we look here, 8 minus J2 and 10 plus J4, these impedances are short-circuited here. Therefore, our Zn is simply 5. So let's go ahead and write that down. Zn is just 5 ohms. To get our, so now we've gotten, so essentially we've gotten our Zn here. Now we need to figure out what our In is, our Norton current. To get the Norton current, we need to short circuit this here. Okay, so if we short circuit that, then we can apply mesh analysis. So what we're going to do is we're going to short circuit A to B, and what happens is we get this line, and this is what the circuit becomes. So now we want to figure out what our In is. Okay, a couple of things to notice. We can do mesh analysis here, so we got I1, I2, and I3. However, we have this current source here, so this is a super mesh. Now let me undo that. We have a super mesh. Okay, so let's go ahead and solve for this. So for the second circuit there, let's look at mesh 1. And then mesh 1 we have minus J40 plus 18 plus J2. I just went ahead and added those impedances together, times I1, and then in the negative direction we got minus 8 minus J2 I2, and then we got our I3, which is minus 10 plus J4 I3 equal to 0. Alright, so that's what we get from mesh 1. Now for the super mesh, we can write this out. We got 13. Okay, so we got 13 minus J2 times I2 plus 10 plus J4. Again, I'm combining them. I3 minus 18 plus J2 I1 all equal to 0. Okay, and then note that at node A, so let's look at node A here. We have the current source between mesh 2 and 3, meshes 2 and 3, so we can say our I3 is equal to I2 plus 3. And then we can further simplify, combine some of these equations. We get minus J40 plus 5I2 equals 0, which gives us I2 is equal to J8. Okay, so now we know, well, I2 is equal to J8. We know that I3 is equal to I2 plus 3, so we can back substitute that in there. Let's go ahead and do that. So we get I3 is equal to I2 plus 3, which is just 3 plus J8. Okay, so we got I3, we got I2, and now our Norton current is just going to be IN is equal to I3, which we just said was 3 plus J8, and this is in amps. Okay, so we solved for our Zn for Norton, that's 5, our impedance, and then our current is 3 plus J8 amps, so technically we've solved for IN and then Zn. Okay, so then the Norton equivalent circuit with impedance at terminals A, B, we can come up with, we look at this circuit here. So we got 5 ohms just coming from there, and we got 3 plus J amps coming from there. So this is our Norton equivalent circuit, and then we can further define this here given the impedances. So we got I0 I naught is equal to 5 over, we're looking for I naught there. Okay, we can use current division to figure that out. So current division. So I naught is going to equal to 5 over 5 plus 20 plus J15 times IN. Okay, so we got our current division, so we got 5 over 5 plus 20 plus J15 times our IN will give us our I naught. So let's go and plug those in. So we got 3 plus J8 over 5 plus J3. We'll plug all those in, and then we can convert that to polar, which is 1.465, 38.48 degrees amps. Okay, and this is our I naught. And that's the final answer using the Norton equivalent methodology for this circuit. So we figured out our I naught, we got our impedance, Norton impedance, we got our Norton current, and then from there we were able to get our I naught across those terminals A and B.